Fire. Next behavior, let us say, is olfaction. So you've got a swarm of robots. Olfaction is a problem in single and multiple robots as well. We'll only discuss the swarm one. You've got either one odor source or many odor sources. And the robots need to go there, which is practical because if there's a gas leak, toxic gas leak, the humans are not going to go and locate the leak with all their sensors. I'm not going, no matter how much security gear they give me, as well as it's a large area, so the humans cannot really work for prolonged hours in dangerous areas to get to the odor sources. I get scared when there's a LPG gas leakage at my house as well, although I have to go and check it up and call for the engineer. So that's olfaction. Now we'll assume that, of course, the detectors are there, the mine detectors are there, the toxic gas detectors are there, and equivalently all the detectors are there. So this is an omnidirectional gas source, and there are detectors all the way up into the robots that will detect this one. And to make it simple, let's only have one detector per swarm. And let's assume that they do come up in actually this ad hoc network thing makes my life at every stage very simple. The robots can actually locally communicate the information. So what we will do around over here is that every robot receives how much is the olfaction, how much is the odor reading. So the detector at every robot detects the odor intensity. And that's the information that I have. And they're all connected. So since every robot is connected to all others, that means effectively every robot knows about each other's odor intensity. Now, let me use a direct algorithm, although we will look at it much later into the course, and therefore I might just skip this one here and currently assume that there's a single odor source. A very practical algorithm, that's the particle swarm algorithm. If you already know this algorithm, you would have seen it's working only in optimization. This time we're applying it on the physical robot. So there the particles would have been something virtual. Here they are, every particle is a real robot. So let's write it down. So a particle means a real swarm robot. So what really happens is, let's do it for this particle. Let's call this robot as Q. So every robot Q shows or knows so every robot Q, it actually knows, the first thing is the best odor source position it has seen so far. This is called as the personal best. So every robot has been searching for odor for quite a long time. Sometimes odor intensity would have increased, sometimes it would have decreased. So it knows where did it get the best odor source. Number two, it knows the best odor source any robot has seen at any point of time. So all the robots can talk to each other and say which this is the star robot, this is the one which has gone closest to the source, called as the global best. And of course, another behavior that I have is that says, so let's talk about behaviors. At any point of time, I can basically have a behavior which says go to not the goal, there's no goal, or the other source is not known, personal best position. The second behavior could be go to global best position. The third behavior could be go to random position, which is what I always add. In particle swarm optimization, randomness is by a different means. And last one is keep going in the same direction. Now, when you have multiple behaviors, you have two ways. Either you apply a selection, that's what we did in the sequencing of the behavioral finite state machine. I first go to A, then I go to B, then I go to C, then I go to these. At any time I go to one place, or you can apply fusion. That's what we did in potential field. Obstacle avoidance, one behavior. Attraction, goal seeking, another behavior, you take a weighted addition of them. And here's, that's why I do. So I say W1, W2, W3, W4. I take a weighted addition of all the four final behaviors, and this is my final behavior. Where W1, W2, W3, W4 are random weights. Now, I'll not stress much upon particle swarm optimization for now. That's a separate lecture, but that's exactly what happens, that this particle has noise. So it saw previous something good over here. It wants to go here, but then there's also this particle which has good order value. That's a global best. So this particle instead wants to go around over here, which is this one. This one is a bit confused to go on its personal best, say it happened over here, or to go for the random one, which is around over here, or basically keep going in the same direction. So from here it went here, so go around over here. But when it goes around over here, it's global best receives, it's getting closer. So it global best also attracts everyone, and everyone is also repelled to go on their own personal best. And finally, you'll see that some particle will, or some robot will actually go around over here as a mixture of these behaviors. The interesting thing around over here is that you could have this same algorithm even when there are multiple multiple order sources with no change, except for what you need to do is that whenever a robot goes very close to this one, it goes very close to this one. So this one is found. The intensity is extremely high. When the robot is at the order source, the order values will shoot like crazy. So what it really does is, if it can repair it up, then after the repair, there's no odor. Like the gas agency that I'm booked with, there's odor of gas leakage. The vendor comes and repairs it up. then automatically nobody gets a traction over here. They only get the traction over here. That's done. But if this robot does not have the capability to correct the order, then of course it will call for human help by buzzers, by alarms. That's the same alarm when you try to nick out something from a shopping mall. The security is called by alarm, by a intelligent system, not intelligent. So of course it'll do all that, but then for all the other robots, what it does it sends repulsion waves. Now you know how to do repulsion. Okay, so this one is gonna send out all the repulsion waves, and everyone knows repulsion, it's something that you need to avoid. So nobody's gonna come here again. There might be some attraction due to this odor if it's not unattended, but this repulsion is always higher, like bright red light. It's danger, just go away. And therefore nobody is gonna come here, all a bad music. So again, everybody just go away. It's bad music, it's frequency that you should avoid, so everybody goes away. These are still very attractive, and now the global bets also change, the local bets also change, and everybody tries to go around this one and this one. So eventually this robot, it appears, will actually have a very high attraction on this one, so it's gonna eventually cover it up and then again repel other robots. Similarly, some of them is gonna cover this one, send repulsion. Now there's nothing to do, but the robots don't know about it. We don't know the number of odor sources. Nobody knows. So they're gonna act random. It's an adaptive system, so the moment a new odor source gets developed, it's gonna be immediately gonna get customers, and they will all try to locate here. Other than that, they'll move randomly. Random is gonna be the force because there's gonna be no update in the odor values, and that's how olfaction happens. Now, one interesting thing is that we previously said that localization is something very expensive, and we know that many robots cost more because the localization systems are like very costly. That's why we use LiDAR and other high proximity, other high cost sensing, high precision sensing. If you really need a budget indoor localization system which tells where the robot is, you create your own homemade GPS system. So that's how it goes. Have a Wi-Fi router here. Have another Wi-Fi router here. And say have another Wi-Fi router here. And there's a robot over here. It wants to approximately know its location. And what does it do? It knows intensity from this Wi-Fi router. Every Wi-Fi router has a signature ID. So from it, it approximately knows the distance D1 here. So around this, cast a circle of D1. It knows approximately D2 distance around over here. Cast a signal of this D2 over here. Cast a signal of radius circle of this D3 over here. And by this triangulation, of course, you'll not get the exact location. It's a budget router, and it's relying on this Wi-Fi antenna. And this one will pick up a lot of noise. Based on this, its position will be the most accurate. But then that's exactly how GPS works. That is exact fundamental of GPS as well. And these are satellites, and they provide up to 10-meter accuracy, sometimes worse than that. If you're going in certain locations where GPS does not come, then it can be a denial of service. The GPS doesn't know where you are, it's not getting signals. GPS cannot have pass-through concrete walls, but currently everything is indoors. Now, unfortunately, if you're using this for swarm robots, then it's no longer an uncontrolled environment where I could just take out my packet of swarm robots, power them up, and just throw them. What you literally throw them. Now I can only throw them if the system is there, but if you have, then you can actually refer to the actual approximate positions of all the robots. The robots, through this triangulation, they know their position, and the others will be by wireless ad hoc networks where they'll transmit their position and ID, so they can do those kind of algorithmics. It's rare that you will need this kind of localization system ever, but then now we talk about swarms with a lot of capabilities, and some of the algorithms may need the absolute positions approximately. So you approximately know that, okay, there's a robot at a distance and you somehow need to go there because it's looking at something interesting. So on the Wi-Fi, on the radio channel, you get its approximate location as per its sensing, and you just say that, okay, that's approximately my location, so I know approximately where to go. That's a budgetary localization system. In fact, even with robotics, so we do have a lot of expensive robots and they have high precision localization and mapping. But then what if I just need a robot that does a lot of things and it's completely budget? So that's one of the localization systems that people do consider, and it's not very accurate. You cannot do precision algorithmics with that, but then of course it does make the robots do everything that an expensive robot would have done otherwise with a lack of precision. A robot will actually collide. It won't be able to go through narrow gaps and stuff like that. But I mean, the good thing is that robot is still working on a budget. Otherwise, who'll buy expensive robots?